Welcome back. In this video, we're going to be learning how a computer uses these same basic principles, such as binary and these mappings of patterns of bits, to represent not only numbers and letters like in the last video on Ascii and Unicode, but how to represent colors, images, and videos, specifically by way of a system known as RGB, or red, green, blue. If you haven't watched my videos on binary or my video on Ascii and Unicode, I highly suggest you watch those before watching this video so you have a better understanding of how this really works. I'll leave a link to both of them in the description. As a quick refresher, in the last video we learned that computers have inside them billions of these transistors that can either store electricity to represent a 1 or choose not to store electricity to represent a 0. And typically we group 8 of these bits together to form a byte. And with these bytes we can represent numbers using binary, and as of now in the story, letters and emojis by way of a system like Ascii and the more modern system Unicode. Well, humans have also standardized a system called RGB, and again, RGB stands for red, green, and blue. You may have seen this if you've done any work with web pages or graphic design or anything to do with art. This system of RGB is essentially going to allow us to represent colors using some amount of red, some amount of green, and some amount of blue. Similar to how we mixed primary colors in art class to make secondary colors, we can think of RGB as having 3 different values, and to represent each color we'll be using 3 bytes total. 1 byte to represent the total amount of red, 1 byte to represent the amount of green, and 1 byte to represent the amount of blue that we should mix together to get the final color we want. And with this system we can represent every color of the rainbow as well as different shades and hues. So let's look at some examples. Suppose we have the values of RGB of 72, 69, and 89. And I'm going to write it like this from now on, with RGB open parentheses, the values, and the close parentheses. And you can think of these values as being the input to an RGB algorithm that's going to give us the solution or the output as the final color when we mix these 3 values together. So if we have 72 red, 69 green, and 89 blue, and we mix these 3 values together, we're going to get this purplish hue. And if you think back to what I said, each value is represented by 1 byte or 8 bits, and that would suggest that each of these values can be represented with a number from 0 to 255. So as an example, if we wanted a solid red color, we would use RGB 255, 0, 0 to represent as much red as possible, but no green and no blue. Conversely, if we wanted to represent solid blue, we would use RGB 255, and if we wanted to represent green, it would be RGB 255, 0. Now, it's impossible to remember every single value and how they're going to mix to give us colors like orange or yellow, for example. So there exist these RGB color code charts that can be found with a simple Google search. And now that we can represent colors, we can start to think about how we can compose an image using this system of RGB. And I'll propose that we think of our computer's screen as just a big grid of pixels. With today's technology, we tend to have screen sizes of 1920 by 1080 or 1440 by 900, and these values just represent how many boxes or pixels the screen is going to be broken up into. And we can see these individual pixels if we zoom in really close on an image. You can start to see each of these pixels is just an RGB value that represents some color. And when we zoom out and get those pixels really small, they start to blend together. And when we look at them with our human eyes, we see a sharp image. But under the hood, all that's really going on is that every pixel of an image is generally consuming 3 bytes, which each represents some color of the rainbow. And this is why picture files tend to be so big. You can actually do out the math, and if you have a picture that is 360 pixels by 640 pixels, that would suggest that we would have 230,400 pixels total. And again, each pixel is represented using 3 bytes. So if we multiply that by 3 bytes, we see that a very small image file can consist of 691,000 bytes, or 675 kilobytes. Now, thankfully, we have fancy compression algorithms that can help save space, and more on that later. But this would seem now that our computers have the ability to represent numbers, letters, symbols, colors, and images. And with these building blocks, you can start to think of what a video might be made of. Well, it's just a series of images that are changing over time. Usually they're changing so fast that it looks like motion picture, but in fact it's just a bunch of images represented in this same way using some kind of system like RGB to represent every pixel, and these images are just changing very quickly. You may have heard the term FPS, or frames per second, if you're into video games, or if you've seen it somewhere else. And most consoles nowadays use a frame rate of 30 FPS. And all that means is that every second that's going by, 30 different images are being put on the screen, and they're changing so fast that your eyes and your brain perceives it as though it's moving. And now you can probably imagine why our video files are so much bigger than our picture files. We have hundreds, if not thousands, of images, which all use 3 bytes to represent each pixel on the screen. And on top of those videos, there's usually some sort of audio track that goes along with it, and then maybe some other features. So now that we understand how computers represent all this different data, we can probably piece together how a computer would store something like sound or music. And if we use these same primitives, it would seem that we could just create a mapping of different patterns of bits and bytes to represent sound. For example, maybe we have one value to represent the note, one to represent the duration, one to represent the tone, and etc. And again, humans have standardized how we do these things. We're not going to get into the weeds too much about these systems, but there are systems like MIDI or MP3 which have standardized how audio is represented inside a computer. And I want to bring up one important point. Let's suppose that we have the ability to see the physical zeros and ones in our computer's memory, and we pull out this 3-byte pattern. What do we really have here? Well, if we convert it to decimal, then we see that we have the numbers 72, 69, and 89. And if we convert those to Ascii, we get the equivalent of HEY, or hey. But if we convert it using RGB, we get this bluish purplish shade. So how do we know what this data is used for? And this is kind of where file extensions come in. If you've ever seen at the end of a file name something like .txt or .png, this is what's telling the program how these binary values should be interpreted. If the pattern was in a .txt file or a .text file, then we should open up a program like Notepad, and we're going to see the ASCII equivalent values of hey. However, if we have this pattern and it was in a JPG or a PNG file, we're probably going to see a single pixel that has a bluish purplish color. And again, this is just to say that it is up to the program and ultimately the programmer to decide how these values should be interpreted. So this has been my video on the representation of colors, images, and videos in a computer using RGB. And really this concludes how we're going to be representing these inputs and outputs into the black box of sorts. And in the next video we're going to start to focus on the black box itself, and really on algorithms and how we can write these step-by-step instructions to solve a problem. I hope you got some value out of this video, and in the next one we're going to be looking at some very simple algorithms as well as basic programming constructs that we'll be using in all of the following lessons.